Okay, so we're discussing mineral and energy exploration, which is a rather large field. So in the olden days, before we really knew much about these things, we would wander around until we'd bust something off with a rock hammer and see that there's some minerals in there and then start digging a hole. Since then, we found that there's actually a science to this, that geologists go out and explore. And initially, our exploration of Australia was, for instance, we went to Broken Hill and found that there's huge outcrops of what they call Gossen, which is the German word for iron cap. That means when you deeply weather a terrain, the sulfide minerals in it will react to leave behind iron oxides. And if you dig into that iron oxide, you soon find that there's lead, zinc, silver, and many other things in there. And so the biggest ore deposit that we ever found in Australia through our first 150 years was Broken Hill, and it's still being mined today. The other big thing that we found was up in Mount Isa. We found a huge lead zinc deposit, and again, that also outcropped. So when you're looking for outcropping mineralization, it's very different than looking for buried mineralization. In these cases, because they outcropped, there was clear evidence in the surface. And so if you take a hammer and start busting around, you realize you should start digging a pit. You dig the pit deeper and deeper. Eventually you get into material that is pristine sulfide. As you're aware, sulfides are not stable at the surface, so they weather away to iron oxides and acid mine drainage, which is a whole other topic for another day. But these big finds we made without any geophysical techniques, in other words, no airplanes, no satellites, we simply went and found them. What you want to do is go out and see as much ground as possible to look to see if there's any anomalies in any metals. So in the old days, that meant panning the rivers because that was the only real way to find them. So you'd work your way up the rivers trying to see if you could identify gold nuggets or platinum nuggets or anything else that would remain as a nugget. However, most of the other things like lead, zinc, silver, copper, etc., these things don't remain as nuggets. So what you do is you go and you hire a junior geologist and you send him to go out and fill a bag up every 100 meters. And you do a grid of soil sampling. And most geos that you meet, including myself, when we were younger, we would be sent out to the middle of nowhere to walk every 100 meters and fill the bag up until we had a backpack full, and do this day after day after day, send it off to a lab, and then plot those results up on a 3D grid and look for anomalies. When you have an anomaly, in the old days you dig a big hole, but now we don't do that anymore. We bring a drill rig out. And the initial drilling we do is where you just drill up chips. We call it RC drilling, which is reverse circulation. You have a big tank of water, you have a very rough bit on the end of your very short drill stem, and you just work your way down, lubricating with the water, and as the water comes out, there's chips of rock that's busted off, and you collect some and look at them. So every 10 meters or 5 meters, you would get some, put that in a bag, have that analyzed in a laboratory, and then go all the way as deep as you can, which is only hundreds of meters, and look for some anomalies to see if it looks like a good place to drill. If you don't see anything, there's no evidence of sulfides in the chips, and there's no anomalies showing up in the geochemical database, you would then probably move somewhere else and stop looking there. However, if it's looking promising, you then get a bigger drill rig in where you drill core, where you have a beautiful round diamond bit which drills a spherical tube through the ground and then brings up the core, which you then take and put in trays, you take back to the lab, you cut it in half. You typically send half to assay, and the other half you have a geologist, a junior geologist again, log the core. What are the minerals, what are the rock types, etc., etc. So on the one hand, you're describing the environment, deposition, and if it's igneous or metamorphic, or what minerals you have there. On the other hand, you're checking it chemically to see if there's some lead or some silver or some whatever it is you're looking for. Right? So that means that core drilling, for most of us that are geologists, is what we prefer. And here's a piece of core that has been cut in half and polished up. And this is from a potential gold mine. and you can see that there's sulfide, so they've come into it. So you just, as a geologist, if you look at a piece of coral like this, you know you're getting some action. This is where you want to be digging further, right? So you keep drilling. Now when you want to then, you say, okay, if you hit, let's say 50 meters of 4% copper, you're going to get the stock market excited, and you're going to get money. You're going to raise money, you can borrow money from the bank, and you're going to have to drill dozens of holes to define the resource. So once you've established the resource there, if you have a hole here that's quite rich, you need to go here and here and here and here, and keep drilling until you're through it, and you've worked all the way around so that you can make a three-dimensional model. If you get a three-dimensional model on a computer these days, and an average grade, then you know how much is there. Then you know if it's worth mining or not, and how you're going to mine it. Whether you're going to make a giant open pit, just dig a huge hole, or whether you're going to sink a shaft for about $1 billion and work your way around it, so it better be worth a lot of money. So that's kind of how the exploration business works.